Hello everybody, my name is Ethan. Welcome back to the channel where today we are going to be continuing our learning on the machine learning course in Codecademy. In the previous video we talked about logistic regression and we have been doing a huge regression unit. As you can see here, Supervised Learning 1 is the chapter that we are kind of on right now inside the machine learning fundamentals. So right now we're about 1/5 of the way through the course, just about over 20% of the way through the course. But we're going through a lot of the content heavy parts of the course with linear regression, multiple linear regression, and then logistic regression, which are just these huge units. And next we are going to have our K nearest neighbors part of the course. You can see we've got a good amount of stuff to go through, so I'm going to get started right away. Excuse me. With the introduction. Before diving into the K nearest neighbors algorithm, let's first take a minute to think about an example. Consider a data set of movies. Let's brainstorm some features of a movie's data point. A feature is a piece of information associated with a data point. Here are some potential features of a movie data point. The length of the movie in minutes. The budget of the movie in dollars. If you think back to previous exercise, you may imagine movies being places in that two-dimensional space between those numeric features. There could also be some Boolean features that are either true or false. For example, here are some potential Boolean features. Black and white, the feature would be true for black and white movies and false otherwise. Directed by Stanley Kubrick, the feature would be almost false for every movie, but for those few movies that were directed by Kubrick, it would be true. Finally, let's think about how we might want to classify a movie. For the rest of the lesson, we're going to be classifying movies as either good or bad. In our data set, we've classified a movie as good if it says it has an IMDb rating of 7.0 or greater. Every good movie will have a class of 1, while every bad movie will have a class of 0. To the right, we've created some movie data points where the first item in the list is the length, the second is the budget, the third is whether the movie is directed by Stanley Kubrick. And then let's add another movie to the code. Add the variable Gone with the Wind. So we'll do this. Gone with the Wind. I think this was me accidentally putting in all those ADWDs, to be honest. And then we'll create that list. It wants to have a 239-minute runtime. 38 or 30, yeah, 38. A budget of $3,977,000, and it was not directed by Stanley Kubrick, so we can give it the keyword of false. Cool. Distance between 2D points. In the first exercise, we were able to visualize the data set and estimate the K nearest neighbors of an unknown point, but a computer isn't going to be able to do that. We need to define what it means for 2 points to be close together or far apart. To do this, we're going to use the distance formula. For this example, the data has 2 dimensions, the length of the movie and the movie's release date. Consider Star Wars and Raiders of the Lost Ark. Star Wars was 125 minutes long and was released in 1977, and Raiders of the Lost Ark is 115 minutes and was released in 1981. The distance between the movies is computed below, so the distance formula here, and that's equal to 10.77. So we're taking the distance between the runtime and the years. Write a function named distance that takes 2 lists, movie 1 and movie 2, as parameters. You can assume that each of these lists contain 2 numbers, the first number being the movie's runtime and the second number being the year the movie was released. The function should return the type of the distance between the 2 lists. Remember, in Python, x power star to the power of 0 will give you the square root of x. Similarly, we'll give you the square, right? So it wants us to write a distance formula, or function, sorry. That's going to take in movie 1 and movie 2. And inside, we're going to do a couple of things. It wants to get the first number in the list. And then, so we'll do 4 feature in movie 1. movie 1 run. I believe it was runtime that it's going to be doing. Runtime is equal to movie 1 0, and then actually, what am I doing a for loop for? I'm not exactly sure. We can just get rid of the for loop there. That was a little stupid, but it's fine. We'll say movie runtime 1 is this. Movie 1 year is equal to movie 1 like this. And then we can do the same thing by just doing movie 2 runtime is equal to movie 2 to the index of 0. And then movie 2 year is equal to movie 2 to the index of 1. Then we can do the actual distance formula, and we'll set this equal to distance is equal to, I'm going to wrap it in a parentheses here, and then do another one and just kind of do the formula here where we do movie 1 runtime minus movie 2 runtime to the power of 2, and then we'll add the second variable, which would be movie 1 year minus movie 2 year to the power of 2, and then on the outside of the parenthesis here we'll put it to the power of 0.5, indicating that we want to square root it. And then of course we will return distance from our equation or definition here. Call the function on some of the movies we've given you. Print the distance between, so we can do that by just doing print distance of Star Wars and Raiders. Print distance from Star Wars and Mean Girls. So it looks like it's more similar to Raiders of the Lost Ark in terms of this distance formula that we've kind of constructed. I'm a little interested in to see how they did it. I see. So they immediately just put the distance in, but they did something very similar to what we did in the case of just grabbing all the variables and then doing the formulas on them. Cool. Distance between points in 3D space. Making a movie rating predictor based on just the length and the release date is pretty limited. There are so many more interesting pieces of data about movies that we could use. Let's add another dimension. Say the third dimension is a movie's budget. We now have to find the distance between these 2 points in 3 dimensions. What if we're not happy with just 3 dimensions? Unfortunately, it becomes pretty difficult to visualize points in dimensions higher than 3, but that doesn't mean we can't find the distance between them. The generalized distance formula between points A and B follows as such. Square root of A1 minus B1 plus these difference between A2 minus B2 squared plus, the difference between AN minus BN squared. Here, A1 minus B1 is the difference between the first feature of each point, and blah, 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 blah. Using the formula, we can find the k nearest neighbors of a point in n-dimensional space. We now can use as much information about movies as we want. We'll eventually use these distances to find the nearest neighbor to an unlabeled point. Modify your distance function to work with any number of dimensions. Use a for loop to iterate through the dimensions of a movie. Return the total distance between 2 movies. Okay, so we want to change this up, right? Likely we're still going to want to be returning distance. We're just going to have to actually return the number of deal with the number of features, right? So we'll write a for loop that says for feature in movie 1. So for every feature in the movie, we'll create a return. Okay, modifier to any number of dimensions. Yeah. So we want to go through the features in movie and count the length. let's think. Let's see if we can get a hint. Yeah, I wanted to do a range length movie, but create a variable called to sum the square difference of each dimension and have it start at 0. Then loop through each dimension and add the square difference for each dimension to your new variable. I see. For IDX and wants us to, I assume we would initialize the squared, we'd initialize it as 0 outside of the loop, and then inside of the loop we're going to squared plus equals, and then the difference of the squares, right? Yeah. You can get rid of this hint now. Movie 1 at the index minus movie 2, the same index, to the power of 2. So we'll add the squared difference, and then at the end we'll have distance is equal to square, or I guess I don't need a parentheses, squared difference to the power of 0.5. And I guess we can do that. We've added a third dimension to our movies, print the difference between, alright, we can do that pretty easy if we just print difference between Star Wars and Raiders, and then print between Star Wars and Mean Girls. Distance. They're a lot farther away. Now Mean Girls is closer though, so that's interesting. Data with different scales, normalization. In the next 3 lessons, we'll implement the 3 steps of the k-nearest neighbor algorithm. First, we'll normalize the data, then find the k-nearest neighbors, then classify the new point based on those neighbors. Excuse me. When we added the dimension of the budget, may have realized that there are some problems with the way our data looks currently. Consider the 2 dimensions of a release date and budget. The maximum difference between the 2 movies is about 125 years. However, the difference between 2 movies' budget can be millions of dollars. The problem is that the distance formula treats all dimensions equally, regardless of their scale. If 2 movies came out 70 years apart, it should be a pretty big deal. However, right now, that's exactly equivalent to 2 movies that have a difference in budget of $70. The difference in 1 year is equal to exactly equal to the difference in $1 in budget. Obviously, very absurd. Another way of thinking about this is that the budget completely outweighs the importance of all other dimensions because it's on a huge scale. The fact that 2 movies were 70 years apart is essentially meaningless compared to the difference in millions in the other dimension. The solution is to normalize the data so that every value has a value between 0 and 1. In this lesson, we're going to use min-max normalization. Write a function named min-max normalization. Min-max normalization that takes in a list of numbers named list. Okay, it just wants me to take the one parameter, and for right now, we'll say begin by storing the minimum and maximum values of the list. So we'll do that by saying minimum is equal to list.min. Maximum is equal to list.max. Variables. Am I not doing that correctly? Of course not. Don't know what I'm doing wrong. What the hell am I doing wrong? Oh my god. Create an empty list named normalized. Loop through each value in the original list. Normalize the value and add the normalized value. Adding every normalized return. Okay, so it wants me to create a for loop for value in list. What is there a normalization function? Will be value minus minimum divided by maximum minus minimum. Okay, pretty easy. Finding the nearest neighbors. So we normalize the data, then we find the k nearest neighbors, then we classify the points. So we're on step 2 right now. Now that our data has been normalized and we know how to find the distance between 2 points, we can begin classifying unknown data. To do this, we want to find the k nearest neighbors of the unclassified point. In a few exercises, we will learn how to properly choose k, but for now, let's choose a number that's somewhat reasonable. Let's choose 5. In order to find the 5 nearest neighbors, we need to compare this to an unclassified movie and every other movie in the dataset. This means we're going to have to be using the distance formula again and again, and we ultimately want to end up with a sorted list of distances and the movies associated with those distances. Might look something like that. In this example, the unknown movie has a distance of 0.3 to Superman 2. In the next exercise, we'll use labels associated with these movies to classify the unlabeled point. God, that's annoying. Begin by opening the running program. We've imported and normalized a movie dataset for you and printed the dataset for the movie Bruce Almighty. Every movie in the dataset has 3 features: the normalized budget, the normalized duration, and the normalized release year. We've also imported the labels associated with every movie in the dataset. The label associated with Bruce Almighty is 0, indicating that this is a bad movie. Remember, a bad movie has a rating less than 7.0. Comment on the 2 print lines that you have to run the program after you have. So run it. It's circling for me. It's taking quite a long time. We'll see if it ever actually loads. Wow. It's taking quite a long time. What is happening? Run? Why was that taking forever? So comment out the print lines. Let's create a function called classify that has 3 parameters. The data point you want to name, that you want named, unknown. The data set you were using to classify it, the data, then K. Now put pass. Inside, remove pass and create an empty list called distances. Loop through every title in the data set. Access the associated loop through every title in the data set. Access the data associated. I think I did something wrong, probably. Oh. I see. We now have a list of distances and points. We want to sort this list from largest to smallest before running results. Use Python's built-in sort function to forward distance. I want to say it's dot sort, but it's going to be like sort. No, it's not. Distances dot sort. I swear if you wrap it. It's probably because distances.sort doesn't return anything, so setting it equal to it's going to be setting equal to none. The k nearest neighbor is now the first k items in the distance. Create a new variable named neighbors and set it equal to the first item. Create a new variable named... So now it wants me to create a new neighbors variable and set it equal first k items in the data set. So we want to do distances from the index of 0 to k. Cool. Test the classify function and print the results. How do I test it? Oh, I'm fucking stupid. So whatever movie this is, it says it's closest to Lady Vengeance, Steam Boy, Fateless, Princess Mononoke, and Godzilla 2000. Finally, we're going to count. Oh my god. I'm dying today, you guys. I don't know why, but it's hard to talk right now. The k nearest neighbor algorithm, we're on step 3 now. Classified the new point based on those neighbors. We found the k nearest neighbors and stored them in a list looking like this. Our goal now is to count the number of good movies and bad movies in the list of neighbors. If the neighbors were good, then the algorithm will classify the unknown movie as good. Otherwise, it will classify it as bad. In order to find the class of each label, we'll need to look at our movie labels data set. For example, movie labels at Akira will give us 1 because Akira is classified as a good movie. Well, you might be wondering, if there's a tie, what if k equals 8 and 4 neighbors were good and 4 neighbors were bad? There are different strategies, but one way to break the tie would choose a class at the closest point. Our classify function needs to have knowledge of the labels. Add a parameter named labels to classify. Should be the third parameter it's wanting. Continue writing your classify function. Create 2 variables named numGood and then numBad. Did they remove the return statement here? NumGood is equal to 0. NumBad also equal to 0. Use a for loop to loop through every movie. For movie in neighbors. Title is equal to movie is equal to neighbors. Title is equal to neighbors movie. Remember, every neighbor is a list of distance and title, so the title can be found at index. There we go. Title. How is that possible that it returned? That's exactly what I have, but oh, movie. Use labels and title, find the label of each movie. Use label and title to find the label of each movie. We probably would want to use, you can find the label by using labels.title. Okay, so then labels, title, if labels.title is 0, num bad plus equals 1, else labels title equals to 1, num good plus equals 1. Use label and title, find the label of each movie if that label is 0. Okay, is it just not indexed in like that? Okay, they just changed it from movie to neighbor, that's fine. You just used an elif statement instead of an else. Is that really it? Why does that make a difference? I'm actually really confused by that because it would automatically check if it's a 0, right? And there's only two options, right? It's either 0 or 1. It can't be anything else. So why I would need an else if statement to also check if it's a 1 doesn't make any sense to me. We can finally classify our unknown movie if num good is greater than num bad. So we'll do another separate if statement on the outside here. If num good greater than num bad, return 1. Else return 0. Call classify using the following functions. So we'll do that. Print classify. First one is 0.4, 0.2, 0.9. Movie data set, movie labels. 5. Predicts it to be a good movie. Should predict it's a good movie. Cool. Classify your favorite movie. Now your classifier will be able to predict whether a movie will be good or bad. So far we've only tested on a completely random point. In this exercise we're going to pick a real movie, normalize it, and run through. In the instructions below you're going to be testing your classifier using the 2017 movie Call Me By Your Name. Feel free to pick your favorite movie instead. To begin, we want to make sure that the movie we want to classify isn't already in our database. We can do this by using the in keyword. Begin by printing the title of your movie. Begin by printing if the title of the movie. If Call Me. To do this, you would do movie. I actually don't know how to do this. In cool. Did it. Once you confirm your movie is not in the database, we need to make a point. What if we tried a different one? Oh, it is. Okay, can't do that one. We'll actually have to do name. Okay. Once you confirm your movie is not in the database, we need to make a data point for your movie. Create a variable called my movie. My movie to a list of 3 numbers. The movie's budget. The budget was $3,500,000. The runtime was 132 minutes, and the movie was released in 2017. We now want to normalize this data point. We've included the function normalize point. Normalized my movie is equal to normalize point of my movie. Oh, no, I'm messing up now. I'm messing up for no reason. Can't print this. You'd have to print. And of course I didn't spell it right, so that's why they're having an aneurysm here. Print normalized my movie. Cool. Finally call classify with 3 parameters. Print classify normalized my movie movie data set movie labels, and finally we want 5 of the nearest neighbors. It says 1, so it says it's probably a good movie. Training and validation sets. You've now built your first k-nearest squares or k-nearest neighbors algorithm capable of classification. You can feed your program a never-before seen movie, and it can predict whether its IMDb rating was above or below 7.0. However, we're not done yet. We need to report how effective our algorithm is. After all, it's possible our predictions are totally wrong. As with most machine learning algorithms, we have split our data into training and validation set. Once these sets are created, we want to use every point in the validation set as an input to the k-nearest neighbors algorithm. We will take a movie from the validation set, compare it to all the movies in the training set, find the k-nearest neighbors, and make a prediction. After making that prediction, we can then peek at the real answer that is found in the validation labels to see if our classifier got the answer correct. If we do this for every movie in the validation set, we can count the number of times the classifier got the answer right. Times obviously it got it wrong. Using these 2 numbers, we can compute the validation accuracy. Validation accuracy will change depending on what k we used. In the next exercise, we'll use the validation accuracy to pick the best possible k for our classifier. Okay, so we've imported training set, training labels, validation set, validation labels. Let's take it one of the movies in validation set. The B movie is in validation set. Print out the data associated with B movie. Print B movie's label as well, which can be found in validation labels. Is a B movie a good or bad movie? So if we do, so it wants me to print out the information about the B movie. So if we do print validation set. Oh, what am I doing here? What the hell am I doing? Set at the index of B movie. We're going to try this. That's not going to work. Actually, never mind. It's because we got this. Maybe. Okay, that actually did work. We can also print out B movie. It's going to give us an X here, but that's fine. So it said the B movie was not a good movie. So now we're going to actually define. Let's have our classifier predict whether the B movie is good or bad using k equals 5. Call the classify function. So we'll print classify on B movie data, which was validation set at the index of B movie. The second was the training set and training labels, and at an index or k as 5. Store the results in a variable named guess. So it wants me to say guess is equal to clarify. Perfect. And then it wants me to print guess. So it did get it right. Let's see if our classification got it right. If guess is equal to, okay. So we're going to say if validation labels at B movie is equal to guess, print correct, else print, holy Moses, I can't hit it correct, you guys, I don't know what to say, wrong, so we got it correct, we knew that though. Choosing K. In the previous exercise, we found that our classifier got 1 point in the training set correct. Now we can test every point to calculate the validation accuracy. The validation accuracy changes as K changes. The first situation that will be useful to consider is when K is very small. Let's say K is just equal to 1. We would expect the validation accuracy to be very low due to overfitting. Overfitting is the concept that will appear almost every time you're running a machine learning algorithm. Overfitting occurs when you rely too heavily on your training data. You assume the data in the real world will always behave exactly like your training data. In the case of the k nearest neighbors, overfitting happens when you don't consider enough neighbors. A single outlier could drastically determine the label of an unknown point. Consider the image below. The dark blue point in the top left corner right here looks fairly significant outlier. When k equals 1, all points in the general area will be classified as dark blue when it should be properly classified as green. Our classifier relied too heavily on the small quirks in the training data. On the other hand, if k is very large, the classifier will suffer from underfitting. Underfitting occurs when your classifier doesn't pay enough attention to small quirks in the training set. Imagine you have 100 points in your training set and you need k equals 100. Every single point will be classified the same way. The distance between the points doesn't matter at all. This is an extreme example. However, it demonstrates how a classifier can lose understanding of the training data if k is too big. Begin by creating a function called define. It wants it to be called define validation accuracy. It takes 5 parameters. The 5 parameters should be training set, training labels, validation set, and validation labels, as well as k. For right now, I'm just going to make it pass. Create a variable called num correct and have it begin at 0.0. So we'll do that. We'll create a variable called num correct and set it equal to 0.0. Then we will loop through the movies of validation set. So for movie in validation set. And for right now, print movie, and then I'm going to put break just to make sure it's working, and it's a definition, so I can't do that. I'm a little stupid, and that's okay. It's okay to be dumb. loop through the movies and call classify on using each movie's data, the training set, the training labels, and K. Store the result in a variable called guess. For now, return guess. So if you loop. So guess is equal to classify on movie using the training set and training labels, and then K. And then for now, return guess. Movies data can be found using validation set. Oh yeah, that's right. That should work now. Yep. Inside the loop, compare guess to the corresponding label and validation labels. So we're going to add another loop inside the for loop that says if guess is equal to validation labels at the index of movie, we're going to say num correct plus equals 1. And that's it. I'm just saying if that is what happens, we're going to add it. So now it wants me to, outside of the loop, return the validation error, which should be number of correct divided by the total number of points in the validation set, which is length validation. Find the validation accuracy with K equals 3. Okay, so find validation accuracy with K of 3. On what? I see, just doing that, I guess. Okay, print find validation accuracy with the training set, training labels, validation set, validation labels 3. It says it should take a few seconds to run. We see that we had an accuracy of about 66%, which not too good in my opinion, personally. Graph of K. The graph to the right shows the validation accuracy of our movies as K increases. When K is small, overfitting occurs and the accuracy is relatively low. On the other hand, when it gets too large, underfitting accuracy stops. So it looks like we peak at an accuracy of around 80, maybe, at 0.73% accuracy. Using sklearn, you've now written your own k-nearest neighbors classifier from scratch. However, rather than writing your own classifier every time, you can use Python's sklearn library. Who else would have just a goated library but them? And we can import k-nearest our neighbors classifier from sklearn.neighbors. There are a couple of steps we'll need to go through in order to use the library. First, you'll need to create a k-neighbors classifier object. This object takes one parameter, k. For example, the code below will create the classifier where k is equal to 3. So classifier is equal to k-neighbors classifier, and neighbors is equal to 3. Next, we'll need to train our classifier. The .fit method takes two parameters. The first is a list of points, and the second is a labels associated with those points. So for our movies example, we might have something like the training points, the training labels, and then fit it. Finally, after training the model, we can classify new points. The predict method takes a list of points that we want to classify. It returns a list of its guesses for those points. We've imported sklearn for you. Let's create the object called classifier and set that equal to the kneighbors classifier with n neighbors equaling, and it wants it set to 5. So hopefully I've spelled everything right. That's going to be the one thing, right? Okay, we've also imported some movie data to train your classifier using the movie data set as the training points and labels as the training labels. So we can do that by just doing, I'll use the same variable I use. Guesses is equal to classifier. And then we do the dot predict method, or no. We do the fit method. First, we fit the training data using movie data set and labels. And we want to fit this first. Classifier not defined. Again, the downfall is going to be my typing. It's okay. Classifier. Oh my god. Classifier. We'll get it one time. Third time, right? Let's classify some points. Classify the following movies. Print the classifications. Which movies were classified as good movies and which were, remember these. Precise idea. Okay, so unknown. Do the same thing that they did, is equal to these. So we have one that's 0.45, 0.2, and 0.5. We have one that is 0.25, 0.8, and 0.9. And finally, we have one that is 0.1, 0.1, and 0.9. And then we can use prediction is equal to classifier dot predict unknown one, 1, 0. Cool. All right, we can review now. Congratulations, you just implemented your very own classifier from scratch using Python's sklearn library. A lot of information here, but when we randomize the points, you know, if we used k equals 3, oh wow, what is happening here? Oh, I see. So any points over here will be classified as green points, right? Any points over here, black points, and we can kind of draw and then see exactly where. But if we were to up it to 10, right, it's going to have a little bit harder time telling you what points are which. As you can see right here, this is a good one, a good example right here. This point over here is considered as green, even though the 3 closest I can't really point, but this is a black. Even when we circle around these black points, it's still saying that the closest, any colors around them should be green. So obviously that's not correct. Okay, let's see what's up next. I believe we'll have a quiz. This one only 10 questions. What a possible problem? Yeah, there could be an equal number of classes. What would you expect to happen to the validation accuracy? This increases from 1 to infinity. The validation accuracy go up and then goes down, right? The predict function in scikit-learns takes and it returns a list of predictions. Underfitting happens when K is too big. When K is too big, so larger trends in the data set aren't represented. Yep. Why is normalizing your data essential? So the feature vastly scale does not tell any other features. We learned about that with the millions of dollars and the years. How does K nearest neighbors define what it means for 2 points to be close to each other? By the distance formula. Using the distance formula. By using the distance formula, right? In the following image, K nearest neighbor would classify the question mark as for which K? As a triangle for which K? So it would definitely classify it for a triangle of 1 and as a triangle for which K? So it's saying which K? It would be 1 and 5 probably. 1 and 5, yep. True, false, the K nearest neighbors can work with a data set with 1,000 features. Oh, I tried to click true, you guys, but my body did not let me. Obviously, yes, this is true. Even though it's not in, we can't visualize the space that it's in, we can't actually work with that. That's a mistake on my part. Which is the nearest neighbor to the point 1, 2? So you would honestly want to put the distance formula in for this one. If I had to guess, it's going to be 1. This one's only 2 points away. This one is 2 points away. It's going to be one of these two right here, I believe. Oh, wait, no, wait. 1, 3? Yeah. Never mind. Overfitting happens when K is too small, so outliers dominate the results. Yeah. Perfect. So that one obviously was a mistake. Can work with 1,000 features. That is obviously 100% true. Okay, so it looks like we have a project here, so pretty excited to do that. In this project, we will be using several Python libraries to make a K nearest neighbor classifier that is trained to predict whether a patient has breast cancer. If you get stuck, obviously you do this. So let's explore the data. Let's begin by importing the breast cancer data from sklearn. We will import the function load breast. So we'll do that from sklearn data sets import load breast cancer. Once we've imported the data, let's load the data into a variable called breast cancer data. Do this by setting breast cancer data equal to the function. Okay, so we can do that by just doing breast cancer data is equal to load breast cancer, and I'm hoping we do this right from the very start. Let's see. Looks good so far. Before jumping into creating our classifier, let's look at the data. Begin by printing breast cancer. So we'll do that by saying breast cancer data dot data at the index of 0. It's the first point in our data set. We want to wrap this in a print statement, and it says it also wants us to print oops, sorry about that, breast cancer data dot feature names. Okay, so we get kind of the first row in our data set, which is really nice. And we get all of the different things that means, what these data sets actually represent, or what these little data variables actually represent. It's interesting that they're not separated by a comma in the list here, but I'm not sure why that would be. But we get to see all of that, which is also pretty good. Now that we have a sense what the data looks like, what are we trying to classify? Let's print both breast cancer target and breast cancer dot target names. So I am going to just quickly comment out these. We kind of get an idea of what those are trying to accomplish. But now let's create a couple new print statements that print out breast cancer data dot target, and we'll also print out breast cancer data dot target names. So let's see what this does. We have a bunch of different points, which are just ones and zeros. Was the very first data point tagged as malignant or benign? So we have two obviously variables that it can be. If it's a 0 index, that means it's malignant. If it's a 1 index, that means it's benign. So the first one looks like it is a malignant data point, and that's how it was tagged. So we now kind of understand that's what we're trying to target here. So let's split the data into training and validation sets. We have our data, but we need to split into training and validation sets. Luckily, sklearn has a function that does it for us. Let's import train test splits from sklearn.model selection. Import train test split. So we'll have to call the train test split. If I remember correctly, we have to classify X train, Y train. If I want to remember the data you want to split, use data labels associated with target, the test size, what percentage test size equal to random state will ensure that every time you run the code, the data is split in the same way. It could be any number, use random state equals 100. Right now we're not storing the return value, returns. Okay, so in the next two columns here, we'll be able to do this. So we can go down now as well. And I'm gonna comment out this print line as well. We kind of get the idea of what it does. I'm gonna just quickly save it so it clears up our console here. And then basically what I want to do is create a train test split call, and inside we want to use the data breast cancer data dot data, and then the labels associated with it would be breast cancer data dot target, and then our test size we're going to set equal to 0.2, so 20% of the data will be used for validation reasons, and then we're going to put the random state equal to 100. Finally, we're going to end up using these variables, so we'll set this we'll have the variables training data, validation data, training labels, and validation labels. Okay. And hopefully everything looks like it's working so far. Let's confirm that we're correctly print out the length of training data. So if we print length of training data, and I'll do the same thing and print the length of training labels. They should be the same size is what it's saying. So 455, we end up getting the same size, so that is good. I'm going to just comment these out so that we don't have to use them anymore. Let's run the classifier. Now that we have created a training and validation sets, we can create a k-neighbors classifier. So again, we're going to have to import from sklearn dot neighbors import, and not neighbors, neighbors import k neighbors classifier. So we are going to then create the classifier object called classifier, if I can spell it right this time, right? And we'll do a k neighbors classifier object with the value of n neighbors is equal to 3. So we created the object. Now we can train our classifier using the fit function. Again, we'll do that pretty simply. sklearn makes it incredibly easy. But we can do this by doing a classifier.fit. If I can spell, it would be easy. And then we'll use our training data to fit the function. Train your classifier, the function takes the, so we'll do our training data in and training labels. So that will fit the data. Now that the classifier has been trained, let's find out how accurate the validation is. Call the classifier score function. Score takes two parameters, the validation set and the validation labels. Let's print it. So if we now do classifier.score and we take the validation data and validation labels, we can see, and we should print this out actually. So we'll wrap it in this and then print this out. Looks like we get a good score of 94%, which is obviously really, really good. The classifier does pretty well when k equals 3, but there's a better k. Put the previous 3 lines of code inside a for loop. Put the previous 3 lines of code inside a for loop. The loop should have a variable named k that starts at 1 and increases to 100 rather than k neighbors always being equal to 3. It should be new. You should now see 100 different variables. Which one seems the best? So it wants me to put these 3 lines right here inside of a for loop. So we'll say for put this inside, put the previous code in for loop. The loop should have a variable named k that starts at 1. For k in then we would obviously change this out to the k nearest neighbors equals to k. See if that ended up working. We actually do see 100 variables here. Pretty cool. Which k seems the best? Kind of hard to tell, but especially when it doesn't print out. Actually, what we could do is print k. If we do that, maybe that's a little bit, not capital K, lowercase k, please. Cool. So now this is a little bit better. It actually tells us what one looks the best. And it looks like we start peaking once we get to this 95.61, right? Oh, where'd it go? 95.61, and the highest one looks to be, I mean, these 3 are exactly the same, right? These 3 right here, actually these 4 right here look exactly identical. So anywhere from 47 to 50 looks really identical. We now have the validation accuracy for 100 different Ks. Rather than just printing it out, let's make a graph using matplotlib, import matplotlib.pyplot using pyplot. So from matplotlib.pyplot import matplotlib as plt. So the x-axis should be the value of k's that we tested, and this should be a list of numbers between 1 and 0. I'm now going to get rid of this print statement, to be honest, so that it clears up this space we have. It shouldn't break anything. You can use x-axis should be a list of values of k that we tested. So we'll do plot dot plot. X-axis should be k. You can use the range function. Let's see what it wants us to do. Range 1, 5, we get it. Create a numbers through 1. Okay, wait. So x-axis should be the values of k that we tested. Oh, it just wants me to start by creating. I was very confused because we implemented, but it should be just range 1 through 101. List. I'm gonna just get rid of this for right now. The y-axis of our graph should be the validation accuracy. Instead of printing out the validation accuracies, we want to add them to a list. Outside of the for loop, create an empty list named accuracies. Okay, so accuracy is equal to an empty list. Instead of printing it out, append it to the list. Accuracies.append classifier. I guess we'll do this instead. Okay, and now we can plot our data, call plt.plot. Inside of it, this should be the K list. Second one should be accuracies. And then we'll do plt.show. Huh. Was it importing matplotlib? Ah, you don't import matplotlib. So we would just actually import. Okay, here we go. Okay, so now we can do it. We saw it. Let's add some labels. So we can do that by doing plt.xLabel is equal to k, and plt.ylabel is equal to validation accuracy. Finally, set the title using plt.title. Set that equal to breast cancer classifier accuracy. So when we do that, we'll see this. Very nice. Great work. Very nice. We can try changing the random state parameter, but it looks like we had a couple of different peaks. Oh, even one around 60. I didn't even notice that one. But that's going to do it for that project. We did a pretty good job on that one. Let's take a peek into what is next. Well, it actually looks like there might be more about the k nearest neighbor. So we learned about k nearest neighbors. And there's also a regressor that goes with it. But that'll be for next video. So I want to say thank you so much for stopping by and enjoying this video. If you did enjoy, please be sure to leave a like, subscribe, and I'll see you in the next one. Peace out.